Hello, this is Mayanja Janet and Nahereza Alvin, and welcome to Machine Learning with Python. Machine learning is just a field of study which gives computers the ability to learn without being explicitly programmed. So, in simple terms, to me, this means that, for example, let's say as humans, we learn from past experiences, but for the case of computers or machines, you'd have to give them data from which they would learn from and try and act and make decisions like humans would. So that's basically machine learning. So let's go into the types of machine learning. We have supervised and supervised learning. Under supervised, this is where you're going to give a machine labeled data from which it would learn from. For this case, you would have to give input variables with corresponding output. Such that the machine, for example, if you give it a picture of a black person and tell them this is a black person, of course, the next time after training it, you give it the same picture, it will be able to identify that this is a black person. Input, output. So under supervised learning, we have regression and classification problems. Regression is simply about continuous and numerical data. Let's say estimating and prediction of prices. For example, you have t-shirts of different sizes, different color, different material. We're going to use such features to predict how much each shirt would cost. Of course, according to the quality, it would cost different prices. So that's what regression is about. We have classification. This is where we just deal with categorical data. For example, I want to classify girls who have curly hair, others have long hairs, a problem of that sort. So unsupervised machine learning, we just deal with unlabeled data. Here, a machine is going to learn from data, you give it inputs, but you're not going to give it outputs. It has to learn from that data using patterns continuously. So under unsupervised learning, we have clustering and anomaly detection. Those are some of the algorithms we use. Clustering, you group data that has similar features, like a bucket of this shape, of this size, this color, try to group them into characteristics that are similar. Anomaly detection, you're just trying to see unusual occurrences in the data. For example, outliers, these are just data points that's so far away from other data points in like a data set. So moving on, some machine learning concepts we can talk about. We have EDA, exploratory data analysis. So it should be quick, efficient. You have to make decisions real fast. You don't need to take a lot of time when you're doing EDA. So here you're just trying to find out the data types, the features. You want to classify them. Are they numerical? Are they categorical? Such kind of things. We have data cleaning. Talk about that. Feature engineering. Here, just trying to look to the features, see which ones are necessary. The other features are strongly they're not going to be useful for the machine learning model. Yes. Let's talk about feature scaling. This decides whether the model will perform well. So scaling, we're just trying to make sure that some data is not so dominant over the other. So you're trying to make sure data is in some fixed range. So you use two methods. We have normalization and standardization. In normalization, you're just going to make sure the range of data values is between 0 and 1. So we have standardization. Here, the data, you're just going to make sure that the mean of the data is 0 and the standard deviation is 1. So let me show you quickly how you can perform normalization. We have a formula here. This one is the min-max scalar. So trying to find a new normalized value, you get a random value from the data, subtract it, you subtract the minimum value from the data, divide by the x max, that's the maximum value, minus the mean. So the new value you get should be between 0 and 1. Yeah, so and the standardization, the one for the mean and standard deviation, you'd have to use the formula like the one we use in normal distribution, like find the mean, but at the end of the day, you have zero mean and standard deviation one, but the data can differ. So let's dive into data cleaning. Here, you're just preparing the data. You're trying to find missing values. You're trying to find duplicates. And for the case of missing values, how you can deal with them, you can drop them and just ignore them. And you can use imputation and try to find the mean of the values in the data set and then replace them with the missing values. So data cleaning just helps you to get quality data that you're going to give to your machine learning model to learn from. Yes. So let's talk about models. A model is just a representation of a phenomenon, like a real world problem. Basically, that's just it, nothing much to it. We have deterministic and probabilistic models. Deterministic, this one's just hypothesize exact relationships. That means you know the exact outcome of something like a problem, the exact solution. Like let's say you're trying to add 2 plus 2, you of course know that outcome is going to be 4. So no randomness. Probabilistic models, you have randomness. Like this is where the deterministic and random error aspect comes in. So we have 3 types of probabilistic models. We have regression models and correlation models plus other models. So let me talk about regression. So before we talked about regression under supervised learning, and this just deals with continuous and numerical values. So it shows the linear regression just shows the ratio between variables, and it's going to use like a linear function to do that. So according to this illustration, these are just prices, prediction of prices. So I'd like to talk about the relationship between like a prediction, maybe a cost function using this illustration. We have different data points, and this is a line of best fit, which you can get using the least squares method. And your aim here is that this data point should not be so far away from this line, because this is like our prediction point, this line of best fit. So we must make sure that the random error between the data points here is so small, like the distance. If it is so far away, that is not good. That means that the predictions might be wrong, because the predicted value is so far away from the actual value. So your cost function just is the difference, like that error between the predicted and actual values. So which would be like this point here, that would be like, that's what the cost function does. I'll optimize that, just make sure that it reduces the cost function such that that error is very, very small, such that you get a right prediction value. Yes, so mostly that is what I can say about regression, specifically linear regression. Lastly, maybe I'll talk about the parametric and non-parametric models. These are just part of regression as well. So here you just know what model you're going to fit with the data exactly, what data you're going to fit with the model. And non-parametric, the data is going to tell you how the regression is going to look like. So it's not about the model, what it's going to depend on the type of data you have, and it's going to define how your regression is going to look like. So let me have my colleague take you through the machine learning models, machine learning algorithms.
Yes, my name is Naireza Alvin. As she has said, we are working together on machine learning with Python. And in the interest of time, I'll go straight to k-nearest neighbors. So k-nearest neighbor is it is a simple but powerful supervised machine learning algorithm, and it can be used for both classification and regression tasks. So the idea behind KNN is to classify or predict the value of a data point based on its proximity to other data points in the feature space. So how it works, it calculates the distance between the data point, the new data point, and all the training set using the Euclidean or Manhattan distance. So in this example that I provided here, this is someone predicting the kind of songs they would like. We have intensity and tempo as shown. Intensity from light to soaring and tempo from relaxed to fast. This guy likes fast and soaring music, and dislikes relaxed and light music. So what if a song, I'll call it a new data point, lies in between here, the circles. So to use KNN to classify such a song, to determine if the guy would like a song or not, we'll first determine the K value. It can be any value. Use 5, for example. So if you draw a circle including 5 values around that new song, which is maybe between the circles, and then you calculate the distance from all other data points, the training set, you calculate the distance from them and then to this new data point. So, and then basing on the majority vote, you classify if many of the data points in the new circle that you've drawn are, let's say, green, you classify that he likes the song. If they are red, you classify that he doesn't. Next, maybe the pros and cons of KNN, you can say it is easy to explain, simple to understand, and extremely powerful. But however, the efficiency of the algorithm declines very fast as the data set grows, and it comes at the cost of making the prediction step relatively expensive. Next, we'll talk about the decision trees. So the decision trees relate to making decisions based on questions and answers, or if something is true or not. Should I do this or not? In an instance that maybe you want to go out to swim or to go for a walk, you would first, let's say you want to go for swimming, you would first check if the weather is favorable, or if it's raining, or if it's shining. If it's raining, you won't go. If it's shining, you have to maybe ask some other questions. Maybe would the swimming pool be open or not, depending on a particular day. That is basically how I would explain decision trees in layman's language. So the structure or the terminology of a decision tree, we have the root node. This one represents, it is on the start of the beginning of a tree. You'd call it like the statement you make first, the statement that you make in the first place, that is going before expanding or splitting. So it represents the entire population or sample, and this further gets divided into 2 or homogeneous sets. That action of dividing into 2 or more subnodes, it's called splitting. And then now the decision node, so when a subnode splits into further subnodes, it's called a decision node. From the root node, you get 2 subnodes. So when a subnode gets split into further subnodes, that is called a decision node. If it can't be split further, it's called a leaf or a terminal node, as we've explained here. So pruning, it is the opposite process of splitting. It prevents overfitting. of the model. So here you're removing subnodes of a decision node, and then as we've said, it prevents overfitting. Overfitting is when the model learns unnecessary features, and so it becomes biased to the training data sets, and it can't predict well in the unseen data. So it starts memorizing instead of generalizing. Yes. So this is how you can form a decision tree. I'll go to the next thing in the interest of time. The cons of decision trees are sensitive to noisy data. It can overfit noisy data. Then there is a beauty algorithm. Doesn't yield optimum structure. Then ensemble learning is about combining many mediocre models in one supermodel. The next thing. So talk about random forest. So in a random forest, basically, we are essentially creating a whole bunch of decision trees together. So if any of the made decision trees becomes in a certain instance becomes unwanted, you just ignore it. So it reduces overfitting of the model. I've already talked about overfitting. Then it reduces bias. For bias happens when you are not even splitting your instance space. So instead of all data points, you might see half of the data. Applications of random forest, you can say in finance, random forest can be used to predict if the likelihood of a default is maybe in economics, and predict whether the policy is becoming effective or not. Talk about support vector machines. Support vector machines, it is used to classify, to categorize a bunch of objects into two categories or more. So they perform a classification task by drawing a hyperplane that is in 2D or in 3D, as you can see here. Yes, you're aiming at categorizing a bunch of objects. So that one category goes to the one side and the other goes to the other, as you can see here. It tries to find the hyperplane that best separates the two categories in a sense that it maximizes the distance to the points in each category. The distance I'm talking about in this case is this margin. It maximizes the margin. As you can see, I've illustrated the margin. And talking of the margin, we have hard margin, and this is associated with correct classification of data points. It ensures that data points cannot cross to this, to come inside here, as I'm showing. And then the soft margin is the opposite of the hard margin. So, and these data points that lie on along the margin, they are called supporting vectors. But in some applications, points cannot be separated by a hyperplane. So in such an instance, you augment the data with some nonlinear features that are computed from existing ones. So after then, you find the separating hyperplane in this dimension, as I'm showing down here. And what you do, you use that hyperplane to separate these data points, and then after you project this back to the original space. This is the Kano trick explains this very well. Yes. In the interest of time, I'm going to stop here. Thank you for watching.